In today's class, we'll be beginning with periodic classification of elements. Or simply the periodic table. Okay, so first point, what is the basis of classification of elements? So the modern periodic table or the periodic table that we study about was given by Moseley. Moseley arranged elements in increasing order of their atomic number. In which he created 7 horizontal rows called periods and 18 vertical columns called groups. So, increasing order of their atomic numbers in 7 horizontal rows called periods and 18 vertical columns called groups. So this was the basis of classification of elements. From this we have the modern periodic table, and the modern periodic law says that the physical and chemical properties of elements are periodic functions of their atomic numbers. So, this modern periodic law, wherever we are reading this chapter, while doing this chapter, we are coming again and again across this words periodic. So, why is this term coming again and again? Because there are certain properties of the elements that reoccur after certain interval of time. That is why they are called periodic properties. So why are there periodicity in properties? So what is periodicity in properties? We know that similar electronic configuration results in similar chemical properties, and same or similar mass results in similar physical properties. So periodicity in properties, what happens is, after definite intervals of atomic number reoccurrence of similar electronic configuration takes place. Since elements having similar electronic configuration have similar properties therefore there is periodicity in properties. To understand this better, let us draw the modern periodic table and have a look at it. So, the modern periodic table. We are dividing this into two parts. The vertical columns are groups and the horizontal rows are periods. So there are total of 7 periods, but we'll only be dealing with 4. And there are total of 18 vertical columns or 18 groups. So 1, 2, 3 to 12, we do not deal with this much. They consist of transition elements. Then 13, 14, 15, 16, 17 and 18. This a number system of groups 1, 2, 3 to 12, 13, 14, 15, 16, 17, 18 is the newer or the modern way of numbering them. In the old way, we used to write them in terms of Roman numbers and with alphabets. This was written as 1A, 2A, 3A, 4A, 5A, 6A, 7A, and group 18 was written as 0. This 3 to 12, we had 3B to 7B. Then we had in this portion we had 3B to 7B, 8 as a whole, and we had 1B, 2B. So the transition elements, these groups you did not remember, but what is important is 1A, 2A, 3A, 4A, 5A, 6A, 7A and 0. So basically 3 to 12 had all the B's, 1 to 7 B's and number 8. So the elements we know are hydrogen, that is placed in the first group, Then helium, it's placed in the 18th group. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium and calcium. Okay. The reason for drawing these lines is to make you understand that this portion, whole portion is empty. This portion is also empty. After calcium, the transition elements start. And this, I have left these lines a little extra is because there are more elements down there, but you need to remember this the structures and their presence where they are till number 20, calcium. After calcium we have transition elements. This space is empty. Okay, so next thing we are going to see is a very peculiar behavior of certain elements here. Lithium and magnesium, though they are in separate groups, show similarity in properties. Beryllium and aluminium, again separate groups, show similarity in properties. Boron and silicon, again in different groups, so show similarity in properties. This, since they are connected diagonally, show diagonal relationship and are also called as bridge elements. So we are going to learn about bridge elements. Lithium, magnesium, beryllium with aluminium and boron with silicon shows similarity in properties. So these are called bridge elements. Elements of the second period show resemblance in properties with the elements of third period of the next group. So second period elements show similarity in properties with the elements of the next period of the third period. Second period elements show resemblance with the third period of the next group. So lithium shows with third period element of the next group. Lithium is in first group with the second group. That is, lithium shows similarity with magnesium. Beryllium shows similarity with aluminium, and boron shows similarity with silicon, leading to a diagonal relationship. This relation is called diagonal relationship. So examples are lithium and magnesium, comma, beryllium and aluminium, comma, boron and silicon. So these are three examples of diagonal relationship. There is another peculiar behavior some elements of a group 14 show. This behavior is called allotropy. The ability of an element to exist in more than one form. This is generally shown by group 14, 15 and 16 elements. Example: carbon exists as graphite, which is soft, and also diamond, which is the naturally most hardest substance existing on planet Earth. So carbon shows allotropy as graphite and diamond. Next. Okay. Group 1 elements are also called as alkali metals. Group 2 elements are also called as alkaline earth metals. Group 17 elements are also called as halogens, and group 18 consists of noble gases. These are also some names you need to remember. Group 1 alkali metals, group 2 alkaline earth metals, group 17 halogens, and group 18 noble gases. Now we'll look at the differences or comparison between alkali metals and halogens. So, alkali metals, halogens. first point, or I'll write the name of the points over here so that it takes less space. So first point will be differentiating them according to their valency. So alkali metals are univalent. They have a valency 1. Univalent means valency 1. They have 1 valence electron. Halogens are also univalent, but they have 7 valence electrons. I'll just write +1 and -1 so that you can recall that they lose 1 electron to become positively charged and halogens gain 1 electron to become negatively charged. The second property that we'll discuss is the nature. In nature, first we have that alkali metals are highly reactive. Halogens are also highly reactive. Second, alkali metals, the nature of alkali metals is that they are highly electropositive. And halogens are highly electronegative. Electropositive basically means they lose electron to form positively charged ions, and halogens they gain electron to form negatively charged ions. That's why alkali metals are electropositive and halogens are electronegative. Third point, they are light and soft metals. They are non-metals. So they can be cut with a knife. Halogens, they are gaseous like fluorine, chlorine. Some are in liquid state like bromine at room temperature. And some are solids like iodine. Next is the oxidizing, reducing nature. So, alkali metals, they are strong reducing agents. They are electron donors. Since they have one electron in their outermost shell, they generally tend to lose electron and hence are electron donors and a strong reducing agent. They reduce others. And halogens are strong oxidizing agents. They are electron acceptors. Next, we have the conductivity. Alkali metals are good conductors of heat and electricity. halogens, they are bad or non-conductors of heat and electricity. And the final point, a reaction with non-metals. Alkali metals, when they react with non-metals, they form electrovalent compounds. And halogens, when they react with non-metals, they form covalent compounds. Okay. So this is the comparison between alkali metals and halogens. We'll look at some properties. First, let's begin with alkali metals itself. So alkali metals are called so because this means that they are called alkali metals because they react with water, forming strong alkali. Second, we'll talk about transition elements. Transition elements are all metals. And they possess, or you can say show, variable valency. Variable valency basically means they have one or maybe more than one valency. Like for example, iron Fe2 plus is ferrous and iron Fe3 plus is ferric. There are two valences for iron. Then we have inner transition elements. Are located in the bottom of the periodic table in horizontal rows. When you look at the periodic table, you'll see there is a periodic table and at the bottom there are two separate horizontal rows. That rows mark the inner transition elements. There are two series. One is the lanthanide series which is present in period 6, and there is actinide series which is present in period 7. They are all metals and chemically they they are very reactive. Also to note that actinides are all radioactive elements. Next, we have halogens. So, halogen means salt producer. It is derived from hal, meaning salt, and gen, meaning producer. Why are they called so? Since they react with metals to form salts. Some important notes. The most reactive halogen is fluorine, and the most abundant halogen is chlorine. The most reactive is fluorine, and the most abundant, that is has huge quantities in supply of halogen, is chlorine. Fluorine prevents tooth decay and is therefore added to water supply. And chlorine kills germs and so are added to swimming pools. And iodine is added to iodinized salts. It is a necessary macronutrient. The next we have noble gases. Noble gases have stable electronic configuration and do not react with other elements. Hence, they are also called inert gases. They are all monoatomic gases. Okay. To this we'll add also one important point of what are metalloids. In the modern periodic table, a zigzag line separate metals from non-metals. The borderline elements boron, silicon, germanium, arsenic, antimony, etc. are intermediate in properties. Intermediate means they have metallic properties as well as non-metallic properties. Are intermediate in properties and are called metalloids or semi-metals. There is also one observation that in the periodic table we learned the bridge elements. The third pair of bridge elements, boron and silicon, both of these are metalloids. So, as boron and silicon are metalloids, they form a borderline. So, on the left of boron and silicon we have is metals, and on the right of boron and silicon what we have are non-metals. Hydrogen, though it is present in group 1, is a non-metal. Okay. Now, important point, we'll learn about the significance of period number and group number. Period numbers signifies number of electron shells of an element. Okay, so if you look at a magnesium, the atomic number is 12, so 2, 8 and 2. So there are 3 shells, hence it is placed in period 3. So if you look at any element in period 3, it will have 3 shells. If you look at any element in period 2, it will have 2 shells. And similarly in period 4, it will have 4 shells, and period 1 will have 1 shell. So the period number signifies the number of shells that are present in the element. So, trends across a period from left to right. Number 1 we learn is of number of electron shells. So since in a period the number of shells are same, so in a period if we move from left to right, the number of electron shells will remain same. So say period 3. So as you move from left to right, what is happening is the number of electron shells remains same. As it is period 3, all of this will have 3 shells. And second trend is of valence electrons. In a period, when you look, this sodium has 1 valence electron, this has 2, aluminium 3, 4, 5, 6, 7 and 8. So number of valence electrons on moving across a period from left to right increases by 1. Then we have significance of a group number. A group number signifies number of valence electrons of an element. So in period of 1 means 1 shell. Period 4 means 4 shells, and so on. In group number, group 1 means 1 valence electron. Group 2 means 2 valence electrons. Group say 13 means 3 valence electrons. Group 17 means 7 valence electrons, and so on. Do note that after 1, 2 we study group 13, 14, 15, 16 and 17, and from 13 it will have 3, 4, 5, 6, 7 respectively number of valence electrons. So again here also we'll see some trends. Downing group. Since groups are vertical columns, so the trends of a group goes down. So first point is of valence electrons. So valence electrons in a group, if you see, so group say 14 will have 4 valence electrons. So if you look down a group, all of these elements will have the same number of valence electrons, that is 4. So the number of valence electrons remains same. And number 2, number of electron shells. So for number of electron shells, as we can see, say we take group 16. So this has 6 valence electrons, and for number of shells, oxygen. Oxygen lies in period 2, will have 2 shells. Sulfur lies in period 3, has 3 shells. As you keep on going down, the number of shells keep on increasing by 1. So the number of electron shells as we go down a group increases by 1. This is the significance of group number. With this, we end today's lecture. We'll be dealing with periodicity in properties in detail in the next class.